Welcome back. We're in chapter 16 on nuclear radiation, and in this section, I'm going to teach you how to make a nuclear bomb. Now, please don't try this at home. It was found in the after First World War that as people were starting to work with radioactive elements, that sometimes radioactive elements do not break apart very, very slowly with a alpha particle or a beta particle broken off little by little by little. But in some cases, if you can have a huge element, such as uranium, which is the biggest element you can mine, and you can bombard it, say, with some kind of a particle, you can get that element to break apart into not just an alpha particle, which is a helium nucleus, but you can break it apart into really big parts. So you can break them apart into two elements. Here's an example on this page of a uranium-235, which is not stable, but it's relatively stable. If you can bombard it with a neutron and then temporarily make that very unstable, it will split apart into not just an alpha particle, but a krypton atom and a barium atom. Both of these are huge, big atoms themselves. So this was a huge atom, broken apart, becomes even more unstable, and it shatters. The really interesting thing they found is that the barium and the krypton, if you were to add those together, the weights of them together, they would weigh less than the original uranium that you had. So in this reaction, weight was actually lost. And that is impossible because if you remember the law that says matter can neither be created nor destroyed, whatever you have at the beginning of a chemical reaction, you're going to have exactly at the end of that chemical reaction. There is another theory, a theory of Einstein, that says that E equals mc squared. I don't know if you've ever heard it before. What that means is that energy, E, equals mass time at the speed of light. So if you can accelerate mass, you can actually convert it into energy. And what's happening in this nuclear reaction, if you can make this unstable, it will split with such force and such ferocity that it will actually convert some of the mass of this uranium into energy itself. So 1 gram of this uranium can produce the same amount of energy as 3 tons of coal. So the amount of energy contained just in its falling apart with that kind of ferocity can generate energy. It can generate energy in a power plant that could power people's homes, or it could generate energy in the form of a bomb. And both have been used in the 20th century to great effect. So what's going to happen in this case is if you break it apart, you're going to get some energy, and then you're going to get more neutrons. And these neutrons then, look, this original neutron came in to bombard this uranium element or atom. And at the end, you're not just going to get a barium and krypton broken apart, but you're going to get more neutrons. So if you had enough of this uranium, let's say instead of having 1 atom, you had, a lot of it. You had a pound of it, where that there were millions and millions of these atoms. Every time that you, with 1 neutron bringing in, making this unstable, bringing this apart, now you've got 3 neutrons that can crash into new atoms. So you can get what's called a chain reaction. Okay, so 1 nucleus is bombarded with a small particle. That nucleus becomes unstable, then it shatters into other atoms, smaller atoms, with neutrons of themselves that can then bombard into other atoms, and you can get a chain reaction going. So here's this example that I showed you the picture of uranium-235. When it neutron bombards it, it becomes unstable uranium-236 and then splits into, and this is called fission. Fission is when it splits. So we're going to look at two different types of events called fission, where it splits apart, and then fusion, where it splits together. In both cases, enormous amounts of energy are produced. Okay, so here's an example of the fission. The neutron comes in, makes this uranium-236 very unstable, and then it splits it into krypton and barium with its own neutrons that could do it again. Here's the formula. It's going to make a very unstable 236, which produces these two stable. Both of these are now stable, krypton and barium, plus 3 more neutrons, plus a lot of energy. And that energy used to be mass in the 235 uranium. These two things weigh less than the original did, which seems to break the conservation law, but it goes perfectly with Einstein's theory of energy transference. So the chain reaction, if there's enough uranium so that every time that the 3 neutrons hit more atoms, then they become unstable, and then they will react, and then they produce more neutrons, and then they hit others, and it's just chaos. Okay, so one neutron hits one, making two, and then 3 neutrons are made, which hits 3 of these other atoms, which makes their own reactions, and so on. So nuclear power plants use this, harness this energy to make power. Okay, and remember, any electric power plant is simply just going to turn a turbine. It's going to make some steam. The steam is going to turn a turbine. The turbine is then going to be around some magnets, and then power wires are going to come out of the power plant to the power grid. So they just need some way to make steam. Now, you could burn coal, or you could burn wood, or you could burn $100 bills if you wanted to make a fire, and that fire makes steam, and that steam in water, and then that steam turns a turbine. So in this case, you're using the energy harnessed in uranium or plutonium or whatever other radioactive elements you've got. What causes a power plant to not be a bomb is these control rods. These nuclear rods are essentially taking the additional neutrons so you do not get a like we had here, where you had a one going to the other, so you don't have a chain reaction, as we talked before. Okay, so the control rods are absorbing these extra neutrons, and then you end up essentially getting power. The other type of power that you can get is from fusion. If you can join, say, hydrogens together and make helium, then you can have enormous amounts of energy. The problem is that these protons want to get away from each other. They hate positives, and positives repel. They do not attract. So you can't force them together. It takes an enormous amount of energy to force them together, and normally that's done in stars. The sun is so hot, it's like 100 million degrees. It's so hot that it overcomes the electrical charges and allows those protons, plus the gravity inside of stars are so huge that it forces the matter together, and that's one reason it's hot. And as it forces together, they actually fuse. So helium and other helium, or hydrogen and hydrogen, can make helium. That's the fuel of stars. So that the sun is mostly hydrogen, and then as it's forced together, you've got helium, and then helium is forced together, and then you have bigger elements and bigger elements produced in these stars. If we could do that, we would have no energy crisis. I mean, there would be no problem with energy. Problem is, you have to have 100 billion degrees in order to do it, and every single building you could make would melt if you had something that was 100 billion degrees inside that building. And so right now, that's what scientists are working on. Hope it happens in your lifetime, and I'll see you in class.